So this is going to be the start of chapter 7, 1 and 7.2 for stats. This is actually going to be probably one of two parts because there's a lot into this lesson here. Probably too much for one video. So I'm going to go ahead and kind of split this up into two parts here. So the first part is going to be about getting these confidence intervals, and the second part in another video will be about using them to work backwards and stuff. So let's go ahead and get started here. So inferential statistics is what we're kind of going into here. So inferential statistics are used to, as the name implies, infer something about a situation or get some sort of uh, analysis from the numbers there. And what we're going to be doing here is going to be using it to estimate or test some claims about population parameters. So again, a population parameter is simply a value that tells you about a characteristics tells you about the characteristics of a population. So like for example, the average. The average of a population is a population parameter. So the average height of the American male is a population parameter for American males in the United States because it tells you something about their height. It just gives you a data about their parameters. So we're going to be considering data that follows a normal distribution, like we have been. And the first parameter we're going to talk about is, as we just said, the population proportion. Actually, it's a little different than average. So a proportion is basically the percent of a population that fits a certain characteristic. So for example, the percent of people in the population who own a dog, or the percent of people in the population who are male, or the percent of people in the population who own a home. Those are population proportions. Um, and so we designate these in terms of successes and failures, essentially. So, for example, the percent of people in a population who own a home. A success would be somebody who owns a home. A failure would be somebody who does not own a home. So again, we just say those words just to get the clarity out of the way there. And we have symbols for them. So the p hat is what this is usually called, and that is the proportion of successes of a sample of a population size n, or a sample size n, sorry. So whenever you hear the word proportion, think percent. So proportion is the percent of a population that fits a certain category. Now, if I said, what percent of people in Illinois own a home? Well, that's going to be kind of hard to gather there because Illinois is a pretty decently sized state, and trying to get records on every person who owns a home on Illinois can be kind of tricky. So instead, what we do is we take samples. Remember, a sample is simply a section of the population that you take data from, and then using that small sample, you apply that to the general overall population. And if you do this correctly, you can get some fairly accurate results. So these two values here, p hat and q hat, are the proportion of successes, or for q hat, the proportion of failures for a specific sample size. So n is the number of people that we're actually testing, do you own a home? And then p hat is the number of people that do own a home out of those n people. So p hat is not the population parameter. P hat is not the population proportion. It's the sample proportion. It's what percent of the sample fit, what percent of the sample fit your category. Q hat is what percent of the sample does not or fails to fit your category. And okay, hiccup there, sorry. Remember, these P hat and Q hats are complements of each other. So, for example, if I'm talking about owning a home, and let's say that I have 70% of the people in Illinois own a home, that means that 30% of the people don't. Okay? Or 70% of my sample owns a home means 30% does not. So they're always in complement here. So basically, P hat plus Q hat should always equal 1 or 100% if you're using them as percents. Now, this is what's called a point estimate. So the population proportion, this right here, or the sample proportion, this right here, is the best point estimate we have for a population, which basically means that if you take data on 100 people, and that's the best sample you can get, and you say that 70% of them own a home, that means your best guess for the amount of the percent of people in your entire state that owns a home is 70%. So if I surveyed, again, 100 Illinois residents, and I found that 70% of them own a home, and that's the best I could do, is get 100 of them. Well, that means that if somebody were to ask me what percent of Illinois own a home, or what percent of Illinoisans own a home, I would say 70%. That's my best guess. Now, is it exactly 70%? Probably not. I mean, it's not exactly any number. Like if I say it was exactly 70 or 73 or 75, both those would be pretty quote unquote bad guesses because the chance that it's exactly 70, not 71, not 72, not 70.5, but the chance that it's exactly 70 is pretty slim. So point estimates are good for, overall, uh, scoping out the situation there. But we usually don't want to stick with point estimates. We usually want estimates that are a range. So it'd be much better if somebody asked me what percent of Illinoisans own a home, and I was able to say between this and this percent is my best guess. Because giving a range gives you a little bit more leeway and a little bit more accuracy in your guess, because you're not banking on it being one specific number. You're giving them a range of possibilities that you know is likely to be true based on your statistics. So let's get over how to get that range using this point estimator. So when I say point estimate, again, I'm just simply talking about the population proportion. Okay, that's simply a number that's our best single guess. So requirements for using the method we're about to do here. It simply has to be a binomial distribution. So fixed number of trials or fixed number of samples, independent, two categories, so again, success and failure, all the stuff we've been doing. One thing that we also have to have is at least 5 successes and at least 5 failures. So we have to have at least 5 people that fit our category and at least 5 people that don't. Otherwise, our data doesn't have enough sample essentially to make it work. So we have to have a big enough sample size where we have 5 successes and 5 failures at least, which usually isn't a problem. So let's do this with something that's a little bit more concrete and something that actually happened. This is actually a real case here. Um, and this is testing a claim. So the claim here, it says here, is that we have tactile or touch therapists are people who claim that they can sense a person's energy and then manipulate it to identify or cure various illnesses. So basically, you come in with a cold or something. This therapist hovers their hand over you, feels your aura, and realigns it, and then all of a sudden you're better. That's what their claim is. So to test this claim that they can do this, a middle schooler invited 280 such therapists. Now, she did this with the help of her mom, who was also a statistician. But she invited 280 of these therapists to come for a study, and they did. So what they did here is they said, okay, we're going to have person have them buried off. So we have the middle schooler on one side, and we have the touch therapist on the other side, and there's a barrier between them so they can't see each other. And they wanted to see if the touch therapist could identify the correct hand or the quote unquote source of pain in a blind test there. So again, they kind of stuck their hands out through this barrier, and the touch therapist was to try to guess. Sorry, I'm shuffling stuff around my desk here. The touch therapist was to try to test which hand they're hovering over. So just to draw a diagram here. So let's say here's the barrier. We have the touch therapist on one side, so I'll put T for touch therapist, and then middle schooler on the other side. So we have 2 holes cut out here. The touch therapist would stick their hands through the holes, and the middle schooler would hover their hand over one of them. They wouldn't touch it, but they'd simply hover their hand over one of the touch therapist's hands. And then they would ask the touch therapist, what hand am I hovering my hand over? And the touch therapist would guess either left or right. And then they would record whether they're right or wrong. And they did this many times with each person. So that's kind of the sample. That's kind of the test they went through, because if they are able to sense energy or sense aura, they should be able to sense what hand the middle schooler is hovering over, so that they could realign the energy or whatnot. So it said that out of these 280 trials, they were correct 123 times out of the 280. Okay, which is the best guess for our point estimator. So if you say, okay, what's the percent of the time that the touch therapist would be correct, you'd say, well, about 123 out of 280. Which, if we do some math here, 123 out of 280, and that line is very annoying. So let me erase that here. Erase. So 123 out of 280. If we do that calculation here real quick. So, come on. 123 out of 280. We end up getting about 47%. 0.47. So they were correct about 47% of the time, which means that they were wrong. 1 minus 0.47. Roughly, was that going to be 53% of the time, so 0.53. Okay. So they have a 47% success rate about as our best point estimator, and a 53% failure rate as our point estimator. So we wanted to figure out, okay, well, if they're correct about 40, it should say 40. Hold on, did I enter that in wrong? Hold on. Whoops, that's right. I entered it incorrectly. So let me go back and change that here. It should be 123, not 132. I thought that was a little high for the failure rate. 123 out of 280. I did it again. 1 23 out of 280. There you go. Which is going to be about 0.43 or 0.44, which makes a lot more sense because I had that written right there. So, small calculation error on my part, but I fixed it. So 0.44, which would make this 1 minus 0.44, which is about 0.56, which makes a lot more sense here. So they were correct about 44% of the time. So they were able to guess the hand that the girl was hovering over about 44% of the time, and were wrong about 56% of the time. Now, here's the thing. You might say this in, okay, well, the touch therapists obviously are faking it, or the touch therapists obviously can't do their stuff because they're correct less than half the time. Well, the thing is, they could just had an off day. What's the chance that, they just got these therapists in here, ran this test, and it was just an off day for them? Because everybody has an off day, right? Or let's say that there was something just went randomly along in the experiment. Somebody didn't do some wave their hand right, or the therapist got mixed up somehow, or whatever. We don't know. But what's the chance that they just got 44% as an odd low ball score? What if they're actually, on average, a lot better than 44%? So we're going to test this claim. So testing a claim is basically gauging how significant is your result. So if we're going to test this claim here, we're going to see how significant, or how much can I trust this 44% is actually the right value. And so we're going to do something called a confidence interval. So a confidence interval is a range estimate rather than a point estimate. So a confidence interval is a much better way to describe your result, because again, it gives you a range of estimate, and it gives you a confidence level, or basically how confident you are that your range is correct. Which is a very lowball way of explaining it, but that's essentially what it is there. So usually there are three types of confidence levels. There's a 99% confidence level, a 95% confidence level, and a 90% confidence level. And as you can probably guess, these are basically how confident you are in your range answers, which is a lot better than a point estimator. Because remember, a point estimator, like 44%, doesn't come with a confidence level. Now, you might be saying, well, if this is my confidence levels, why don't I just always choose a 0.99% confidence level? Like, why even bother with 95 or 90? Well, the thing here is that as you go up in confidence level, your range increases. So let's say you're guessing a number, right? Let's say you're trying to guess a number between 1 and 100. I pick a number at random, and I go and say, okay, you give me a range, two numbers, a low end and a high end, and if my number is anywhere inside that range, you win. So you give me one low number, one high number. If it's within that range, you win. Well, if you wanted to be 99% confident, obviously if you want to be 100% confident even, you'd say, well, the number is between 1 and 100. And you'd be right. But that's a pretty wide guess. It means that you're not really confident in that you can actually get the number right. So if you're a 99% confidence level, that means your guess spans a really far range. Whereas if you have a 90% confidence level, that means your guess spans a really narrow range, because there's a higher chance that you're guessing wrong, because you're not giving yourself enough or as much of a wide range to work with. So sometimes 90% is a better confidence level to work with, um, because you're given a smaller range. Even though you're less confident, you have a smaller range of data to work with. So if you're running an experiment or playing with some chemistry or whatever, you have a smaller guess range that you have to take into account. So just because it says 99% doesn't mean that's always the best one to use. In fact, the one that most people use is a 95% confidence level, because it strikes a nice balance between how wide your guess range is and how much of an accurate guess that you're going to get there. So 95% is what we're usually going to go with unless otherwise stated. Now, what does this confidence level to do with stuff? So we commonly express this confidence level using the area on a normal curve, because remember, we are working with normal distributions here. So if we have our normal distribution, right, the confidence level is basically the percent of the area that we're guessing, and then the alpha is the percent of the area that we're willing to be wrong in. So think of alpha as the percent you are wrong. So the confidence level is what percent you feel that you're correct. The alpha, which is what this thing is right here, the alpha is the percent that you're wrong. So obviously the confidence level is equal to 1 minus your alpha, because that's how, again, it's how probabilities work. So if you're 95% confident, that means you're 5% unconfident. So think of the alpha as the unconfidence level. And what that means graphically is that if this is your normal distribution, you're 95% of the area is what you're guessing here. So right here, between this low end and this high end, so this is your low ball guess, this is your high ball guess for your range, that is 95% of your area. Okay? So 95% of the values you're guessing is between this low end and the high end. Whereas here and here, both of these together make up your 5% unconfidence level. So right here is 2.5%, and right here is 2.5%. So if it happens to be here, that means your guess wasn't low enough. If it happens to be here, that means your guess wasn't high enough. But you're 95% sure that's somewhere between these two low and high end numbers here. Now, again, this sounds sort of abstract because I'm dealing with, again, non-concrete numbers. So let's start to put this to the test here. So let's say we have a 95% confidence interval and we obtain the following values: 0.356 and 0.567. So we're testing, say, let's say this is the question: what percent of Illinois, IL for Illinois, IL, what percent of Illinois has blue eyes? Okay. Just picking a random thing here just for some context. So what percent of Illinois has blue eyes? So we ran the data, we did the numbers, which we'll show you how to do here in a second, and we end up getting this confidence level between 35% essentially. So if I take these into percents, this is about 36% and this is about 57%. Again, P here is the population proportion. So P here is what we're estimating. So we said between 36% and 57% of Illinoisans have blue eyes. We're 95% sure of that. So that means that we're 95% confident that in between these two numbers is the actual percent of Illinoisans who have blue eyes. Or to put another way, whatever experiment we did, whatever samples we got, if we did that over and over and over and over and over again, 95% of the confidence intervals we got, of which this would be one of them, would be correct. So it's kind of frowned upon to say that you're 95% sure that the actual percent of Illinois people who have blue eyes is somewhere between these two numbers. That sounds like an easy way of explaining it, but it's a little bit different than that. Because if you're saying it that way, then you're saying that the percent of people who have blue eyes in Illinois shifts at any one moment. And that's not really typically true. Even if you have a person born with blue eyes, it's not going to change the needle that much with one birth. So it's better to think of confidence intervals as saying it like we said here, that you're 95% sure that between these two numbers is the actual percent of people in Illinois who have blue eyes, is between 36 and 57%. So how do you find these low and high end numbers? How do you actually make your interval? And we make them using something called critical values. This is going to be something that's going to be with us for quite a while. So critical values are nothing more than just z-scores. So I often abbreviate them as CV, but they're nothing more than z-scores. They're the lowest and the highest z-score values you can pick to match your confidence level. Because remember, we're making this off of a normal curve. So this is my normal curve, my bell curve there. So the low and the high end guesses are basically, like I said, the z-scores. This is the lowest z-score you're willing to accept. This is the highest z-score you're willing to accept to keep whatever designated confidence interval you're working with, which in our case is usually 95%. So based on your data, what is the lowest possible z-score and the highest possible z-score you can accept to maintain a 95% to guess 95% of the possible values there. And luckily for us, a normal curve is evenly distributed or symmetric. So that means the low and the high end numbers are basically going to be plus and minuses of each other. So if this z-score was negative 1.7, then this z-score would be positive 1.7. If this was negative 2.5, then this would be positive 2.5. So all you really need to do is find one of the z-scores, and then you automatically find the other by just switching the sign. But again, think of critical values as the lowest and highest possible z-scores you're willing to accept, and then we can take those z-scores and make them into actual values or percentages that we can use. Now, again, the z-score you pick depends on how wide you want your confidence interval. If you want a 99% confidence interval, then your lowest and highest numbers are going to be way far out here because you want to guess 99% of the numbers. Whereas if you want a 90% confidence interval, then your z-scores are going to be somewhere in the middle because you're willing to accept a smaller range of guesses there. Now, you can look these up in the table, and I'll show you how to do that. But most tables for z-scores, most z-score tables, have the three common ones listed down on the bottom somewhere. So if you're doing a 95% confidence interval, your z-scores are plus and minus 1.96. If you're doing a 90% confidence interval, your z-scores are plus or minus 1.6, and then 99% is that. So these are often listed on the bottom of your table. And again, this one's the most important one to remember if you're going to memorize any of them, because this is the one we use most often is 95%. So 1.96 plus and minus is your 95% confidence interval z-score. Now, graphically, it looks like this. So again, if this was a 95% confidence level, and this is your normal curve, your bell curve, that means this is the lowest z-score you're willing to accept, which is at negative 1.96. This is the highest z-score you're willing to accept, which is at 1.96. And between these two z-scores are 95% of the data that you could possibly guess. So 95% of the possible data is between these two z-scores. And then that 5%, that alpha, remember alpha being 5%, which is the unconfidence level, that 5% is split between the low and the high ends. Because sometimes you might be too low, sometimes you might be too high. So you split that unsureness evenly between the low and the high end. So let's do one that's not normal here, just so that you know how to make it yourself there. So let's say they want you to make a 92% confidence interval. How do you get your alpha? How do you get your z-scores? Okay, so you have to take this in this format here. 92% confidence level means that your unconfidence level, your alpha, is 8%, or 0.08, right? If you're 92% confident, that means you're 8% unconfident. Now, because you're going to split this between low and the high end, so again, if you're 8% unconfident, that means that 4% is too low and 4% is too high. So you're going to split this in half. So you're going to take that 8%, split it in half, so 0.08 divided by 2. That's why it says alpha divided by 2 there. And you get 0.04. So this is what you're going to use to look up in your table. So think about this 0.04 as being the marker for your low end z-score. So this 0.04 is your low end z-score marker. So that means that you're looking for the z-score. If I erase some of the stuff here, you're looking for the z-score where you have 4% of the data, 0.04, behind it. So how do we get the z-score where 4% of the data is behind that value there? Well, luckily, our z-score table actually does that for us. Because remember, these middle numbers here, that is the area behind the z-score. So we're looking for what z-score has an area behind it of 0.04. So we're going to look here and get as close to 0.04 as we can. So here's 0.041, 0.0409, 0.0401, and then 0.392. So this right here, 0.0401, seems to be the closest we can get to getting 0.04. And that seems to be a z-score of negative 1.75. So that would be negative 1.75 and positive 1.75, because remember, they're plus and minuses of each other. So what that means is that on my bell curve, my low end is at the z-score of negative 1.75, and my high end is at the z-score of positive 1.75. That means that 92% of my possible guesses are between these two numbers, and that means that 4% is too low, or 4% is below my lowest guess, and 4% is above my highest guess. So these are my incorrect zones, and my correct zone takes up 92% of the area of my possible guesses. So we use this to create what we know as a margin of error. So a margin of error is kind of like, in those polls where they say, 12% of people believe this, give or take 3%. So they're often like, 12% of Americans believe that cats don't make good pets. And below they'll have a margin of error, so they'll often give as MOE, margin of error of plus or minus 3%, which basically is them telling you that their best guess of people who think cat makes poor pets is between 9%, which is 3% lower, and 15%, which is 3% higher. So that margin of error is simply how far off their guess that they're willing to accept there. So how do we get that margin of error? Because that's what we're really looking for here when we're doing a confidence interval. Well, we get that by taking our proportion, p hat, and using, whoops, I didn't mean to do that. Try that again here. Using this formula right here. So it's the z-score you got from the previous work that we just talked about, times the square root of percent that you got correct on the sample, percent that you got wrong on the sample, or that didn't follow on the sample, divided by the total number of sample here. So again, think of the margin of error as how far off your sample proportion you're willing to go. So let's say that you have a sample proportion. You're testing how many people in the United States have blonde hair, and you end up with a sample proportion of 60%, okay, 0.6, which means that Q hat, your sample failure, is 40%. And let's say you sampled, I don't know, 1,200 people, okay? You sampled 1,200 people, you got 60% were blonde, 40% were not. Let's say that doing your calculations, you got the margin of error is 0.05 or 5%. That means what you would say is that if somebody asked you what percent of people in the United States are blonde, you would say, well, 60%, which is the same proportion, plus or minus 5%, which is your margin of error. That's how you would display your results there. Or you could say that I'm 95% sure that the uh, percent of people in the United States that have blonde hair is between 60, give or take 5%. Or put another way, what most people would say is that you'd say you're 95% confident that the people in the United States that have blonde hair, or the percent of people in the United States that have blonde hair, is somewhere between 55 and 65%. That's how you would typically state in a study or so, is you'd give the low and the high end range yourself rather than using the plus or minus notation. So lots of talk here. Again, this is what I was just talking about, is how you would write your answer. So if your population guess was 60% and your margin of error was 5, then it'd be 60 minus 5% for your low end and 60 plus 5% for your high end, and that would be your range of values there. Or you can write it with the plus and minus notation like they did there. And usually we round to three sig figs. So let's finally put this into a problem here so you can kind of see how this is done. Okay, we've talked a lot about what to do. Let's actually do it to show you here. Let's take the data we had before. So touch therapist, we ran the experiment, 280 trials, 123 correct. We know that 44% of the time then, the touch therapists were correct. So that's our best single number guess. Now I'm asking you to make a 95% confidence interval so you can tell me with 95% certainty what is your best range of guess for how correct the touch therapist would be. Not a single number, but you're 95% sure that on a typical average given day, the touch therapist will be correct in identifying this hand between what and what amount of time. Okay, so the first thing we need to do is figure out our margin of error. And we get that by getting our z-score. Now, because we have a 95% confidence interval, that's one of our common z-scores, and that's a z-score of 1.96. That is given way back. Come on. There you go. That was given way back. If I go here. So that was one of those three common ones here. And 95%, as I told you, is going to be one of the most common ones. So 1.96 is a good number to know. Now, it is technically plus or minus, but we're just going to stick with the positive version for right now, just because it's easier to work with. Come on. There you go. So that's 1.96 for my z-score, times the square root of p hat, which I found was 44, because this was the sample that they were right. So 44% of my sample got it correct, which means that 56% of my sample, or 0.56, got it wrong. And I sampled 280 trials, right? So divided by 280. So I'm going to crunch these numbers here. So 1.96 times the square root of 0.44 times 0.56 all over 280. And we end up getting 0.0581. So 0.0581. Right. So that is my margin of error. So the way I would display my answer is I would say, okay, my best guess, I'm 95% certain that the touch therapists would be correct in identifying the hand 44% of the time, give or take roughly 5%. Or the way I would write it using the interval notation, which is what this one's called, the interval notation, is I would say 0.44 minus 0.0581 less than p less than 0.44 plus 0.0581. This is where the plus or minus bit comes in. So we just do the plus or minus down here rather than putting it up here. So that would end up being a roughly 0.381 less than p less than 0.497. So in percent form, that'd be 38.1 up to 49.7. So I could say that I'm 95% sure that the amount of times the touch therapist could correctly identify and read a person's aura to figure out the hand that they were hovering over is between 38 and 49%. Now, if we were assessing whether the touch therapist is actually good at, excuse me, if we were assessing whether the touch therapist could actually do this correctly in a professional setting, like if they said, okay, are these touch therapists actually doing it with proper guessing, or are they just guessing randomly? Like, are they just getting lucky? Is there actually some education to this? Can they actually feel something? Is there actually something that's like nudging them in the right direction, or are they just guessing? Well, if you look here, their most generous guess about what percent they're correct, if we're being really generous and giving them the most benefit of the doubt that we can, they're still less than 50% accurate. So even giving them the most benefit of the doubt, they're still just barely less than 50% accurate, which is less than what you'd get if you're just guessing randomly. Like if you're just guessing randomly whether she's hovering over the left or right hand, you only have two choices, right? So you're going to be right 50% of the time if you're just guessing randomly, and they couldn't even do that. So we would say that since 50% doesn't fall within this confidence level, they're doing less accurate work than just randomly guessing which hand that she was hovering over, and therefore we can probably conclude that this supports the fact that touch therapy does not work. We don't say, it's actually, I word this kind of poorly here, we wouldn't necessarily say that we conclude that the therapy doesn't work. We would say that this evidence supports the claim that the therapy would not work. Because maybe this, like I said, maybe there was something that went wrong in the experiment. We don't know. But based on this given evidence and based on the numerology that we used here, we would say that it does not work as evidenced by this. Now, maybe another study comes out and shows that it does work. Then we have to assess that study and connect the studies and make our own judgment there. That's how judgment works. But based on this example and based on this study, the touch therapists are less accurate than just blindly guessing which hand they were hovering over, and therefore we can conclude from this evidence that it does not support the fact that touch therapy work or is effective. So that's going to be it for this video. I know it was a long one. The next video is going to be basically how to work backwards. So if you're given the margin of error, how many people do you need to sample in order to achieve that margin of error? So if you're doing a study and you only want a margin of error of 1%, how many people do you need to survey to get that margin of error of just 1%? So we'll be working on that in the next video. But that's it for this one. It's kind of a long one, I know, but it's very critical to what's coming up here. We're going to be basically doing 3 videos on this, just one for proportion like we're doing here, one for average, and one for deviation. And they're all very similar with a slight tweak in the formula for each different type. So we really want to make sure that we focus on getting on this one down. So review the video again, maybe a day or two later once you have time to digest some of it. It might take a few tries to get it down. But as always, let me know if you have any questions. And I hope to help you out in the next video. So have a good day, night, or afternoon.